two things that I would have wanted to do last time. Didn't have enough time for. So the first one is, so remember after I gave all these definitions about linear systems and complete linear systems, pencils, base point freeness, and so stuff. I didn't really use any of those definitions. So I had wanted to give an example where you can actually see what these definitions mean. I think it's a pretty useful example to have. So I'll do that first. And then I wanted to go over some of the points of the proof of the Kodaira embedding theorem, some of the technical points in some detail. Actually show you some of the computations that go into that. Okay, but so let me do that example first. So that has nothing to do with the embedding theorem per se, but it's just to illustrate the meaning of these definitions of linear systems and base points and so stuff that would have been the fourth example last time. So after the elliptic curves, like the Weierstrass P function and the Kodaira maps on elliptic curves associated to multiples of points. So you'll just restate the definition. So we have compact complex manifold, holomorphic line bundle over M. So V is the space of holomorphic sections. And W is a linear subspace of V. So that's what we'd call a linear system for no apparent reason, so it's kind of a strange name. But again, the picture you should have in mind is that W is a space of sections. The sections have zero loci, and I'm sort of looking at the family of these zero loci, at the family of these hypersurfaces parameterized by the elements of W. It's like a parameterized family of hypersurfaces of my manifold. So if parameterized in a linear way. Right, and so it said that if W happens to be the whole space of holomorphic sections, so if I'm looking at the zero loci of all holomorphic sections, then I'd say that my linear system is complete. And when the dimension of W happens to be 2, so it's sort of the smallest possible non-trivial linear system you could imagine, then linear system is called a pencil. Right. So if the examples of linear systems that I gave last time were all of a very simple kind. So, took a very ample line bundle, looked at the complete linear system, so looked at all the holomorphic sections. Examples very ample, so there's no base points, and the Kodaira map is a nice embedding. So I want to give you a couple of examples of linear systems that behave completely differently. Maybe that's going to explain where this notion of linear system comes from. So I'm going to take M to be the projective plane, and L the line bundle O of 3. So that V is going to be the space of homogeneous cubic polynomials on C3. So that's a 10-dimensional space. So since two polynomials cut out the same hypersurface in P2, cut out the same algebraic curve in P2, if and only if they differ by a non-zero scalar. This is saying that we have like a 9-dimensional family of cubic curves in P2, or that the family of all cubic curves in P2 is 9-dimensional. So that's like the complete linear system associated with L. Now we're going to cut that down. So what we're going to do is we're going to fix a bunch of points in the plane. And then we're going to define a linear system. W, so that's just going to be the space of all cubics that vanish at these points. All of these points. So that's sort of a canonical way of passing to a linear subspace. You're imposing conditions of vanishing, something like that. So geometrically, that just means I'm imposing, I'm fixing a bunch of points, and I'm only looking at cubic curves that sort of pass through these points. It's like the picture of the quadrics I drew last time. Not call all quadrics passing through two fixed points, or if you're taking, if your line bundle had been O of 1, then you would be looking at lines, maybe passing through a fixed point. So that's a linear condition on sections, to vanish at a given point or at a bunch of points. So looking at all the curves that pass through that set of points. You could ask, what is the dimension of that subspace? That's going to depend on K, obviously. So if the intuition is that, since your original space is 10-dimensional, if you just impose, a couple of these conditions, then it's, going to cut down the dimension by the expected number. If you just require that the cubics pass through one point, then surely that's going to reduce the dimension by 1. But as you increase the number of points, so if these things get more and more special, and certainly if you impose too many points, or if you demand that your cubic passes through too many points, then the problem is overdetermined, and there's not going to be even a single cubic that passes through a very large number of points. But there's sort of an intermediate range around 9 points where some sort of unexpected things happen. Right, so I'm going to say that in terms of the base locus. That's maybe the best way to say it. So if my points are sufficiently general, if I'm imposing at most 9 conditions, so that's somehow the limit. This family of cubics is 9-dimensional. Then the base locus of this linear system. So the base locus is by definition the point, like the locus of all points where all of the sections in my linear system vanish. So if the set of all points where all of my cubics in the linear system are forced to pass through, then you imagine if K is reasonably small, then there's just going to be these K points. That's where imposed vanishing, and there's no a priori reason to think that they vanish at other points as well. So the base locus is just going to be, that's actually true, so it's just going to be the set of points. If K is at most 7. And so then when I look at all cubics passing through 8 general points in the plane, there's something funny going on. So, I've got my 8 points, and then there's going to be another point. So what's happening here is that the space of all cubics is a C10. I'm imposing 8 conditions, so I'm cutting down to C2. So after modding out by scalars, I expect there to be like a one parameter family of elliptic curves passing through the 9 points. So that's a pencil. But the pencil is sort of, that's almost like a meromorphic function. It's almost like a function 2p1. So if I want to understand all the curves in my pencil, it suffices to take two of them, like the preimage of 0 and the preimage of infinity. And all of the other curves are going to be linear combinations of the ones in between. But if I have two elliptic curves, so it's 2 degree 3 curves, then Bezout's theorem that I was trying to sell you as a homework problem last week tells us that they're going to intersect in 9 points. So I really only have like a one parameter family of elliptic curves, a linear a pencil, so the dimension of W is 2. So everything that happens is determined by two curves in the pencil, but they intersect in 9 points. So this actually means that all curves in the pencil have to intersect in the same 9 points. So it's like one more common point of intersection than I had imposed initially. And then Fk is equal to 9. Then the base locus is just the unique cubic passing through these 9 points. So the moral is here: if I take 8 sufficiently general points in the plane, and if a cubic passes through 8 of these points, then there's sort of one other point P star that only depends on these 8 points, so that the cubic necessarily has to pass through that point as well. And there's like a one parameter family of cubics satisfying that property. This is the pencil, case of a pencil. So the picture here is you have two cubics, F and G, intersect in 9 points, and then your pencil is just a family, S times F plus T times G equal to 0, where ST is in P1. There's just two interesting special cases here. I mean, this is certainly the most interesting case, the 8 and 9 points. But k equals 6 is a pretty interesting case too. It's a very classical example. So cubics passing through 6 general points in the plane. Right, so you're looking at all cubics passing through 6 general points in the plane, then the base locus of that linear system is just going to be those 6 points. According to the fact that I stated, that's more or less believable. And now the base locus is sort of the indeterminacy locus of the Kodaira map. And we can resolve indeterminacies by blowing up. So if I actually blow up the 6 base points of my pencil, I'm going to get a well-defined holomorphic map from the blow-up of P2 in those 6 points to whatever projective space these guys live in. So it's going to be P3 actually, because I'm imposing 6 conditions on cubics. 9-dimensional family imposing 6 conditions, so there's P3 left. So get the induced holomorphic map from P2, blow up of P2 in these 6 points to P3. Then it's a classical fact from classical algebraic geometry that this is an embedding. So this is an embedding it's kind of clear what the image has to be. It's a cubic surface. So the image is cut out by, it's going to be cut out by a cubic equation in P3. Right, so the picture is that, here's one of my points, Pi. I have this linear system of cubics passing through there. So they all intersect in that point, Pi. But by blowing up Pi, I'm replacing Pi by the space of directions through Pi, that's a P1. And this means I'm sort of separating out all these cubics so that they're no longer passing through one common point. So I've removed the base point. I'm just going to intersect the exceptional curve of the blow-up transversely. Sorry? Oh, yeah, thank you. Sorry, in the second case, is these you start with 8 points, but then there's this other mystery point that the cubics have to pass through. So if you blow up P2 in those 9 points, like in P1 through P8 and the other point P star, then the same thing happens. At each of the 9 points, you're going to have this picture of this one-parameter family of cubics sort of passing through. But this time it's really just a one-parameter family, because in this case the dimension of W is 2, so it's a pencil. And I'm separating off the directions of these curves by blowing up the point. And then I really have like a genuine holomorphic map to P1, like a pencil is a meromorphic function. I've resolved the base points of the pencil. So what I'm going to get is that my surface, so if I blow up these 9 points, then my surface is sort of going to be fibered by elliptic curves. So it's a genuine holomorphic map to P1. And the preimage of each point in P1 is one of these elliptic curves. So it's a fibration of my surface. So get a holomorphic map from to P1. So we call an elliptic fibration of a complex surface. So fibration whose general fiber is a smooth elliptic curve. And this guy here is called a rational elliptic surface. So I think I'm going to be talking about K3 surfaces next time, and this is like, this is 50% of a K3 surface. That's one of the nicer ways of seeing what a K3 actually is. Yeah.
You say that each fiber is elliptic curve?
Uh-huh. Like the general fiber is just going to be one of these cubics in my linear system. One of these smooth cubics. And then there's going to be special fibers, but those are sort of hard to understand.
Special fibers will be some singular.
Yeah, that's like one possibility. If your pencil of cubics in P2 happens to contain like a nodal cubic or something like that, or a cusp, then that's going to pull back to a special fiber of the fibration. But there's sort of more complicated things if you're. Here I've drawn the cubics as intersecting transversely. But so if they intersect like with multiplicity at some point, then you have to blow up more than once. And that's going to give you more complicated special fibers than just singular cubics.
Does it happen for general position of P1, P8?
Yes. Maybe not for very general position. Okay, so that's these linear systems. So So the other thing I wanted to talk about is some other aspects of the proof of the Kodaira embedding theorem. So in this case, our line bundle is positive. This Hermitian metric with positive curvature. Sort of sketch to you is this construction of Gaussian sections. So I have my line bundle raised to some high tensor power. It's going to be L to the K, where K is very large. Then I have these localized sections of the line bundle. So if you look at the section with the kth power of the given Hermitian metric, that's section S, and then hk of SS is going to be something like, roughly, k to the n over 2 times e to the minus k mod z squared over 2. If this is my base point and my coordinates are centered at that point. So that's the profile of the section, and the higher I raise the power k, the more localized the section gets. So it sort of converges to a delta function as k goes to infinity. The point is it gets more and more holomorphic as I'm increasing k, because the thing was constructed using a local trivialization. And then I just, pushed it forward to the manifold and cut it off with a smooth cutoff function. But sort of all this cutoff error is supported here, where the section is exponentially small. So the only region where the section is not actually holomorphic is some sort of annulus around here. But as k goes to infinity, the section just, concentrates around the center. So the failure of the section to be holomorphic is supported here, and it's sort of exponentially small. So these points. So these are the only points where d bar of my section is not 0. So then it's actually going to be true that d bar of the section, if I measure that in L2 with respect to my fixed Kähler metric on the base and this Hermitian metric L to the k, h to the k on the line bundle, L to the k, then this is going to be O of k to the n over 2 times some random constant here, but something that goes to 0 exponentially fast. Yeah.
How do you choose this k?
Tell me again.
How do you choose this k? And eventually you will have to choose some k.
Yes. So first of all, the section isn't precisely holomorphic, so I want to make it holomorphic. That's the step I actually want to talk about, okay? So then you want to know that you have the section which is almost holomorphic, so you want to perturb it to become genuinely holomorphic, but you still want to maintain it this sort of Gaussian shape, right? So you want to be the correction kind of small. And so one thing that determines k is to ensure that the correction is actually small. So if the accuracy gets better as k gets larger, and then in the next step I'm going to say that fix k sufficiently large, and then it's actually going to be true that this correction that makes a section holomorphic is so small that it basically keeps the same Gaussian shape. And then of course I want to know that I want to construct an embedding, so I want to construct these Gaussian sections based at lots of points. So I want to take a very large and very dense finite set of points in my manifold, and at each of them I want to implant one of these Gaussian sections. So this is eventually going to tell me that I have an embedding on that large finite set of points. But then I want to say that I also have an embedding in a small neighborhood. That also has to do with the choice of k. That's sort of a more complicated argument. So I mean, I have an embedding on a very large discrete set of points, and then I want to say in a neighborhood of each of these points, I actually still have an embedding because the differential is injective. So that's going to be true once the peaks are high enough.
I'm kind of confused. You just start with a smooth bump function S, and then you say that it is not holomorphic only on the n-limits?
No. So what I did is I trivialized the bundle locally, okay, and I claimed, so that's actually going to be homework today, I claimed that I can choose the trivialization in such a way that this weight function of the Hermitian metric, so if I write the Hermitian metric as e to the minus phi, then that phi can actually be chosen to be roughly like a quadratic polynomial. So that's like, that depends on, choosing the right trivialization for my bundle. Once I have the right trivialization, what I do is I just take the constant section, so if the trivial section is constant equal to 1 in the trivialization, and I push that forward to my actual line bundle. So it's actually just a constant section, but if I measure its norm with respect to the Hermitian metric, that's going to look like a Gaussian. So this is not actually the graph of the section, this is the graph of the length, the norm of the section as measured with respect to Hermitian metric. So the actual section is just the constant section 1. And then I cut that off with some random cutoff function. But you don't even see the effect of the cutoff function in this picture because the length of the section with respect to that Hermitian metric is already exponentially small here. So no matter what the cutoff function does, it's just, you almost don't see it anymore. But as a section, it's just sort of the constant section 1 and the right kind of trivialization. So then what I want to get to is this this idea that sounds kind of silly at first. If you want to solve a PDE, d bar s tilde equal to d bar of s. Solutions to PDEs can be non-unique, and what you want is a good solution. Sort of, you want to say that you have a well-posed problem, that if the right-hand side is small, then you're actually able to find some solution that is controlled by the right-hand side. So you want to solve the PDE with estimates. That the solution S tilde, solve that for S tilde with an estimate, sort of S tilde, the norm of S tilde in whatever sense, is at least controlled by the norm of the right-hand side. So since this is kind of exponentially small in k, as long as I have some uniform control on that constant, once I take k sufficiently large, it's actually going to be true that the norm of S tilde is going to be as small as I like, given that that constant is uniform. And then sort of for k sufficiently large, S minus S tilde is a desired holomorphic section. And so the more general problem that I'm going to show you how to solve, more generally, hope to be able to solve, we call that problem star. So that's d bar alpha equals beta with an estimate beta is a 0, 1 form with values in L to the k, and d bar beta is equal to 0. So if that's a more general problem you can solve. You want to solve d bar alpha equals beta with control, and beta is given to you. It's a 0, 1 form with coefficients in my line bundle. Just think a 0, 1 form. And it has to satisfy an obvious necessary condition, which is that d bar of beta has to be 0. I mean, here we actually know that beta is d bar s, so we already know that it's d bar of something. but that sort of extra information isn't actually useful. Sort of all that we would need is, d bar beta equals 0. Let's first remark, so the extra information. So that beta is actually d bar of something isn't useful. It's got to come out of the proof that this, had to be true anyway under all of these assumptions. And the second remark, so just want to state that more formally, already mentioned it last time, is that, solving this problem is like an effective version of the Kodaira vanishing theorem. With estimates. Okay, so Kodaira vanishing. For the experts, this is a statement that if H is an ample line bundle on a compact complex manifold, then the cohomology of M with coefficients in K sub M tensor H is 0. So that's actually true for all positive degrees. And now you want to apply this with H equal to Km dual tensor L to the K. So you want the cohomology with values in L to the K to vanish, so you have to tensor with the dual of the canonical bundle here. And the point is that, L, this is ample. But this guy might not be ample. Usually it's not going to be ample. So you have positive curvature here, and you're adding on some negative curvature there. But the point is the amount of possible negative curvature here is fixed, and here it gets multiplied by k. So by making k large enough, putting so much positive curvature on this factor that it's going to swamp all the possible negative curvature from this factor, and then H is going to be an ample line bundle, and then Kodaira vanishing applies. This is going to be positive once k's are sufficiently large, depending on M. This is the algebraic version of going about this proof. So the first step in the actual proof of star is to reduce this to proving an inequality. So I'm not going to show you how to do the reduction, but I want to show you how to prove the inequality, at least in a special case, because that's what really, that's what matters, the estimate, and not sort of the formalism that you use to reduce to that estimate. So the first step, show an inequality. So that's going to be the statement that for all 0, 1 forms with coefficients in L to the k, it's going to be true that integral alpha squared is less than a constant times this thing here. If k is sufficiently large. So the picture is that here that you have sort of the sections of your line bundle. You have 0, 1 forms with values in your line bundle. You have 0, 2 forms. That's in the line bundle. You have the bar operators that go up here. So if you don't like this whole coefficient business, like taking coefficients in the vector bundle, just forget about it. Pretend that the line bundle is trivial. That's the most interesting case anyway. Then you have sort of adjoints of these operators with respect to the various metrics that we've chosen. We're somehow only interested in this piece. I'm claiming that for all 0, 1 forms, it's actually true that I can control the L2 norm of the form by the L2 norm of its del and the L2 norm of its del bar. So the del of the 1 form lives here, and the del bar and del bar star. So if the del bar of the 1 form lives up here, it's a 0, 2 form. The del bar star is just a 0 form that lives down here. And I'm not going to explain to you why exactly this is the right inequality to prove, or the right a priori estimate to prove. I could just show you right away that this has, this inequality has one implication that is sort of consistent with what we're trying to do. The thing is, Hodge theory tells us that once we've chosen metrics on our manifolds and bundles, and sort of cohomology groups with coefficients in the bundle can be represented by harmonic forms. And a harmonic form is just one for which del bar is 0 and del bar star is 0. So if I have a harmonic form, then this inequality would tell me it actually has to be 0. So there are no harmonic 0, 1 forms with coefficients in that bundle, meaning that there is no degree 1 cohomology with coefficients in that bundle, and that's sort of exactly what we're trying to do, but with estimates. And since this here is an estimate, it's maybe not so surprising that, if you set it up the right way, you're actually going to get not just the vanishing of cohomology from this, but actually with an effective estimate over there. But that's the key thing that needs to be proved. So this inequality and I want to show that in one special case. So if you want, that's going to be line bundles on elliptic curves. So I'm going to be assuming that my manifold is one-dimensional, that's the Riemann surface, and I'm also going to assume that this form omega sub h, the curvature form of my line bundle, is a flat area form or flat metric on M. So this basically leaves only one case. So this leaves the case that M is an elliptic curve, C mod c plus c tau. And omega sub h is, the standard form, I guess, 2 pi times I over 2 times dz bar, dz wedge dz bar over the imaginary part of tau. So in that case, you can actually do all the constructions explicitly. You can write down your line bundle explicitly and write down explicit Hermitian metrics whose curvature form is this. So what I'm saying is that the curvature form of the Hermitian metric is supposed to be positive definite, so it's a conformal metric on my Riemann surface, and I'm saying that this metric is supposed to be flat. So there's a holomorphic coordinate z, and it's just really a constant multiple of the standard form in those holomorphic coordinates. If you want, you can also pretend that the line bundle is trivial. So then this means that you're sort of either working locally just on a disk in the plane, sort of with zero boundary conditions, or you're working on the elliptic curve actually, but you're sort of you're ignoring the topology of the elliptic curve. Just want to be thinking about a trivial line bundle so that these you don't have to be confused about what these coefficients actually mean. So the important thing is the metric. The important thing is to have a metric of positive curvature. So this inequality is about 0-1 forms with coefficients in L, but L, I'm sure pretending that L is trivial now, so 0-1 form with coefficients in L is just u times dz bar, where u is a smooth function, complex valued function on my Riemann surface. So it's the advantage of having these global coordinates. So I'm going to be proving an inequality for smooth functions after throwing out all the formalism. This inequality dagger actually just becomes the following. It's going to be part of your homework. uz minus phi sub c times u squared e to the minus phi is bigger or equal than a constant times integral u squared e to the minus phi. So that's the inequality I need to prove for all smooth functions u on my surface. This guy here is just d bar star alpha norm squared. So the point here is, of course, that to define what d bar star means, I had to fix a Hermitian metric on my line bundle, but I told you what the Hermitian metric is. So the Hermitian, maybe I didn't tell you. That's the point. So the Hermitian metric is really just e to the minus phi mod w squared. So I'm pretending that the line bundle is trivialized, so the Hermitian metric can be written as e to the minus phi times some weight. And so the exercise is to check that this guy here, this expression here, is actually d bar star with respect to that Hermitian metric. And this is just the norm of my one form, the norm squared of my one form, with respect to that Hermitian metric on the line bundle. It's a trivial line bundle, but with a non-trivial Hermitian metric. And technically, so if you want to prove inequalities, all this Hermitian metric stuff comes down to is to put a weight e to the minus phi under all your integral signs. So to prove a weighted L2 estimate as opposed to an ordinary L2 estimate. This is sort of all what these Hermitian metrics really mean. Stick a weight e to the minus phi in everywhere. And of course, these are integrals over M. And the area form I'm integrating with respect to is just the area form I'm chosen, the flat area form. you can take it to be, or you can, I mean, not necessarily, but you can. That's certainly a valid example. Take, it's some you have some phi whose dd bar is equal to this, at least locally. That's a perfectly fine example. And now this is just an inequality for two functions on the complex plane, phi and u. So how can you go about proving something like that? Proof of this. Also the sort of uz minus phi zu times uz minus phi z u bar times e to the minus phi. That's what's on the left-hand side. Now, that's your exercise to show that this operator here, so it's a first-order operator on u, that's actually d bar star in this formalism, so it's the adjoint of the d bar operator. Meaning, I can throw one d bar on the other side. So this is the inner product of d bar star with itself. So I can pull one d bar star off the left-hand side and put a d bar on the right-hand side in return. So this is the definition of d bar star. That this is, I guess, so there's some issue with plus and minus sign in this business. So I'm going to leave out all the signs. We have to reintroduce them. Come back in the right way. This is so I'm taking the operator off the first factor and putting the adjoint operator on the other factor. The adjoint operator is just d bar. So what I'm going to see is that I have a uz minus phi zu z bar e to the minus phi. And the point is it's a weighted adjoint. It's an adjoint not with respect to the Euclidean volume form, but with respect to this weighted volume form e to the minus phi dz bar. This means that I don't actually have to, if I do an integration by parts, I don't actually have to differentiate the phi anymore because that's already hidden. It's a weighted adjoint. This is why I have a derivative of phi in here. So then I work this out. What is this? This is, under the complex conjugate sign, it's going to be uz z bar minus phi z z bar. There really is a minus sign in front of this. U minus phi z uz bar. And now you see two things. This is the curvature of the line bundle. Okay. But what is the rest? So it's uz z bar minus phi z times uz bar. So this kind of looks like this guy here, but this operator here, but applied to u sub c bar instead of u. It's like I have a u z bar differentiated by z minus phi sub c times u z bar. So it's the same operator as here, so it's this d bar star thing, but it's hitting u sub c bar instead of u. But notice formally, if I want to view it that way, I have to switch these two derivatives. And this is where I'm using that my metric on the base is just a flat metric, so I can just flip these two derivatives without any curvature terms. So this is in general, flipping these two derivatives here is in general where, this Kodaira business, the canonical bundle would come in. But I'm assuming that I have a flat metric, so meaning the canonical bundle is trivial and doesn't have any curvature. So that's in this Kodaira business of the contribution from the manifold, from the metric on the base. E to the minus phi is the metric on the vector bundle. That's something. So, it's only to do with the geometry of the bundle as a fiber bundle, but the flipping the derivatives here is where the geometry of the base would come in. But here I'm assuming that the geometry of the base is flat. So this is minus u times u sub c bar.
So sorry, this will give you some explicit amount of how big we need k to be?
Yeah, exactly. Though in this case, I'm assuming that the base geometry is flat, meaning that the canonical bundle is trivial, so every positive k is actually going to work.
But in the general case,
Yeah.
if you have a controlled curvature.
There would be a Bochner formula here that involves the Ricci curvature of the base. That's right, and then k would depend on that. Minus z bar plus there's e to the minus phi here as well. And this is just what I was saying before, so that's actually the, so if you want, that's the d bar star operator applied to u sub c bar. But then I'm using the adjoint property again, so I'm moving the operator to the other side. It's plus or minus the d bar star, but the way it actually works out is that it goes on the other side with a minus. So the minus sign goes away. So it hits with a d bar on the other side. So actually what you're going to get is u sub c bar squared e to the minus phi plus integral phi sub cz bar u squared e to the minus phi. And this is the good term. This gives you the one, I mean, if you're assuming that your curvature form is precisely equal to your metric on the base, then this guy here is just 1 with our coefficient. But in general, this is what's going to give you the good thing. So this gives you this eigenvalue gap, e to the minus phi. And this term here is positive, so it's not a bad term, but you don't actually use it for anything. So this is how these estimates work. And that's just a good computation to think about, keep staring at it until you see what's actually going on. So there, I'm going to write down the principle more abstractly. Yeah, sure. Because if you take the adjoint of you're taking the adjoint of d bar. Okay, so you're taking the adjoint of a first order operator. So that's like minus the same derivative. And the adjoint of u sub x is minus u sub x plus stuff. Sure, you can, but if you actually express what the adjoint means in local coordinates, then the adjoint of u sub z is going to be something like is minus u sub z. Okay, so I'm just going to write down this principle more abstractly. So you have some operator t, and you want to compute the norm squared, the L2 norm squared, or some Hilbert norm squared. And this is going to be the same thing as t star u squared plus commutator term t star t u. It's almost a tautology, but the idea is that this at least has a sign, so it's not a bad term, but you don't particularly care. And from this commutator term, maybe if you're lucky, you're going to be able to extract some sort of positive constant. So you hope that this is bigger than. So this is a quadratic form basically associated with a commutator of your two operators, and so you're hoping that this quadratic form has a spectral gap. And that's what's going on. If you take the d-bar operator and its adjoint, the commutator of the two is a curvature term. That's what's going on. And that's sort of a principle that that's valid much more generally in analysis. So that's the idea of a Kalaman inequality. So people who look at more specifically, for Kalaman inequalities, your inner product, your L2 norm is going to be something like e to the minus phi times the volume form. So that's sort of the idea that works for a lot of differential operators. That if you take a weighted L2 norm where the weight is sufficiently complicated, then actually this commutator here is something. If you choose the right kind of weight, is something that you're going to be able to bound from below. That you get a spectral gap from here. So this is a technique that's used a lot for people who study unique continuation theorems for differential operators in various contexts. So it's almost a universal technique that gives good results in many contexts. And these L2 estimates are due to Hermander in the 50s, I think, and this is where Hermander was coming from, sort of in analysis. Okay, I guess my time's up for today, so I made a couple more homework problems. So maybe some of them here. So I wanted to talk about Kähler metrics today, and some of the problems use that. I didn't manage to, but anyway, so it's a problem for today and tomorrow.